Hello everyone, welcome to this video. In this video we are going to look at another example of group. So here in the previous video we have talked about a group which consists of integers modulo n, right, under the operation of addition modulo n, right. In this video we are going to see multiplication modulo n. What properties does it have? Does this form a group or not? So let's move ahead and see this thing. So for this we consider z5 star. Now this star represents that we are talking about the multiplicative group, and here in this case we do not take 0, because if we take 0 here and if we try to find the inverse of the number 0, it would be 1 by 0, which is not defined. So we do not consider 0 in this particular case, correct? So we consider the set z5 star. It consists of all the elements 1 2 3 4 less than 5, which are less than 5 starting from 1, right, and the operation that we use is multiplication modulo 5. So this is the symbol that we use. Now what do we do for this operation? Suppose we have the two numbers 3 and 4 and we wanted to calculate their multiplication modulo 5. So what we are doing here is we are just multiplying 3 and 4 and we are taking their mod 5. So what is 3 into 4? That is 12. So we are calculating 12 mod 5. So 12 mod 5, this is equal to 2, because 2 is the remainder which is obtained when you divide this 12 by 5, right? So you have 2 here as the remainder. So whatever is the remainder, that is your answer in this particular case. So now with this calculation and with and by knowing that how this operation works with the given elements of the set, we have to check that these two combined together, do they form a group or not? So let's proceed. For proceeding, what we do, we construct a Cayley table, because we have finite number of elements here and the operation is also given to us. So for the Cayley table, we write all the elements as row wise and column wise here, and then we just fill up all these boxes one by one, right, by performing the calculations that I have just told you. So once you reach at filling up this table, so let me show you how we do this. Suppose we wanted to do it for this element, so we basically wanted to construct it for 3 multiplication modulo 5 3. So what is this thing? This would be 3 into 3 mod of 5, right? So this would be equal to 9 mod of 5. So when you divide 9 by 5, so when you divide 9 by 5, it would give you 4 as the remainder. So your answer is equal to 4. So this is what we have written here. In a similar manner, we fill up all the entries of this table one by one, and once you write by your own all these gray entries by yourself, now we need to check the properties of group. So it's very easy with this Cayley table, because we have most of the calculations written here with us, and because you are not quite compatible with for solving these calculations just by looking at them, for example, as we do in addition, simple ordinary addition and in ordinary multiplication. So here we construct this Cayley table, so it helps us to identify the properties. Just like in the closure property, we wanted to see if we take two elements from the group, from the set, and apply this operation, does whatever is the resultant, does that result also belong to the set or not? So here we basically are seeing at the results. So we have these elements and these elements. So when we apply multiplication modulo 5 onto these elements, we obtain these elements, these 16 elements. Now if you can see all of these 16 elements, either they are 1 or they are 2 or they are 3 or they are 4. So therefore they all belong to this set of addition modulo 5, right, z5 star. So therefore the property of closure holds. Next is the property of associativity. So basically in this property we wanted to check that A addition modulo 5 with B, and then addition modulo multiplication modulo 5 with C, right? This is equal to A multiplication modulo with 5 and performing first B multiplication modulo with 5. So let's see what is this. here it is associative. Why? Because we are essentially performing the multiplication, so it does not matter whether we perform these two first or these two first, right? So this operation, in fact, multiplication modulo 5, that is associative in nature, that is known to us previously. And for an example, I have chosen these three numbers 1, 2 and 3 from this set Z5 star, right? And we will check that whether this thing is it equal to this thing or not for these three elements. So let's solve it. First of all, we'll solve this much portion. So what we are doing, we are multiplying 1 by 2, that is 2 only. 2 mod 5 is 2 only. So 2 mod 5, multiplication mod 5 with 3, that is 2 into 3, that is 6. So 6 mod 5 is equal to 1. And similarly, when you solve the second portion, so first of all, we have to solve this 2 multiplication modulo 5 with 3. So it is 2 into 3, that is 6. 6 mod 5 is 1. So we have 1 multiplication modulo 5 with 1. So 1 into 1 is 1. So 1 mod 5 is equal to 1. So you see both of them, they are equal to each other. Hence we have the property of associativity. But we need to check it for every element. But that is quite not possible, because we have so many combinations here for choosing 3 elements out of 4. So we have these many combinations here. So therefore it would be very difficult to check it for each combination. So we say it is associative because we know that the operation here, this one, is associative in nature. Correct? Now for the third part, we wanted to see what is the identity for this. Does the identity exist? If it exists, what is it? So for that, if we suppose any element from this set, and then we need to find some element from the same set, such that when we do multiplication modulo 5 of this element A with the element E, right, we obtain A. So this is our goal here. So here we clearly know that E is equal to 1, that is the identity from the Keller table. Why? Because we are looking for these particular elements, we are looking for the exact same copy. So the exact same copy is obtained here, and it corresponds to the element 1. So E is equal to 1 here in this case. Similarly, for the second case, for these elements we have the exact copy here, and it again corresponds to 1. So therefore E is equal to 1 is the identity of this particular set, right? This is clear from the Keller table. And lastly, we wanted to calculate the inverse for each of the elements. So for that, we take certain element A, right? Now we need to find certain element B from the same set, such that when you apply A multiplication modulo 5 with the second element B, it will give you E, right? And what is E? E is equal to 1. So we have 4 elements. We wanted to calculate the inverse of each of these 4, 1, 2, 3 and 4. So let's go back and look at our Keller table. Here we need to find what is the inverse of A. So that means we need to find something here such that it is equal to the identity, which is 1. Next, we wanted to calculate this thing, and similarly for the element 3, and similarly for the element 4. Why? Because here 1 is the identity of this particular set and group together with this operation. So here for 1, we need to see which result will give us 1. So here we obtain 1 and it corresponds to 1. So that means here we should write 1. So that you can now say 1 is the inverse of 1 only. It is the inverse of itself. For 2, we have to look for such an element such that the result is equal to 1. So the result is equal to 1 for this one. So we have corresponding to it 3. So 2 is the inverse of 3. What is the inverse of 3? So for that, we will look at the row for 3. Here in this row, we will look at what is the result. When do we have the result as equal to 1? So we have it 1 here, and it corresponds to 2. So that means 2 is the inverse of 3, 3 is the inverse of 2, 1 is the inverse of 1. And similarly, to calculate the inverse of 4, we will look at the element whose result is equal to 1. So you see we have 1 here, and it corresponds to 4, so that means 4 is the inverse of 4 only. So now we have the inverse of each of the elements within this particular set, so therefore we say inverse of each of the element exists for this group and for under this same operation. So now because all the 4 properties, closure, associativity, identity and inverse exist, so therefore we say Z5 star under the operation of multiplication modulo 5, that forms a group, right? And moreover you should note that in this case the set, this Zn, it is the set of non-negative integers which are less than n, right? So this set we considered when we considered the operation of addition modulo n. So we started with 0 and we stopped our set at the last point was n minus 1. Similar to this, we can now construct Zn star, which is nothing but a subset of this set Zn, right? And what is this? This is the multiplicative group where we have Zn modulo n as this is the multiplicative group for the above group Zn, right? In this group what we do, we remove this 0, and moreover what else we do, for the set of integers we write all the values between 1 and n such that all the values should be relatively prime to n, so that means they should have nothing in common with n, right? For example, if you take Z10 star, so here 10 is not a prime number, right? 10 is a composite number. So in this set we will write all the elements starting from 1 such that they have nothing in common with 10, right? So the number 1 does not have anything in common with 10, so we will write 1 here. Now 10 and 2, they have 2 in common, so therefore we cannot write 2 here. For 3 and 10, they have nothing in common, so we can write 3 here. They are relatively prime to each other. Then what about 4? 10 and 4, they have 2 in common, so we cannot write it here also. Then 5, 10 and 5, so it has 5 in common, so we cannot write 5 also. What about 10 and 6? They are also not relatively prime to each other, so we cannot write 6 here. What about 10 and 7? Yes, 7 and 10, they are relatively prime to each other. Nothing in common exists between these two, so we can write 7 here. And what about 10 and 8? For 10 and 8 we have 2 as common, so we cannot write this one here because they are not relatively prime. What about 10 and 9? 10 and 9 do not have anything in common, so we can write 9 here. So these are the elements that we obtain in case when n is 10, which is not a prime number, and in fact it is a composite number, right? Next, what is the case when n is prime? So when n is prime, we have Zn star. This is the set which contains the elements from 1 to n minus 1. Now why is this so? Because if you have n as prime number, so every number which is less than this number would not have anything in common with it. Why? Because this corresponds to the definition of prime number. A number which do not have any common factor is a prime number, right? So therefore, because 11 is a prime number, so you can write 1 here, 2 here, 3 here, 4 here, 5 here, 6 here, 7, 8, 9 up to 11 minus 1, that is 10, right? So, and you can observe that all of them, they are relatively prime to 11, so that means they do not share anything in common with 11. So this is the set. So whenever you have some prime number, you can very easily write down your set, and this set together with the operation of multiplication modulo, that creates a group. And moreover, in certain books and literature, this thing is also written as this Z mod nz cross. Cross represents the multiplication group, otherwise it would form the addition modulo group, right? So I hope you understood this example of addition and multiplication modulo. These are quite important examples and will be repeatedly used in the course ahead. So I hope you understood this concept. Well, that is it for this video. Thank you for watching.